No, thank you so much. Thank you for inviting me to come be part of this. This is so exciting, and I'm learning things along with you because this isn't my normal playground. So thank you so much. And
why is it not showing on the screen?
we'll find out. But that's okay because I can just keep talking anyway. So today, what I'm going to talk to you about. So generally, yeah, I wear a lot of hats, but the biggest thing that I do is if someone asks me, like, what is my core identity? I am a nomadic mathematical modeler. I am a person who goes, tell me your question, I can turn it into math, and then we can play with the math and figure out what that means. And so I'm going to tell you today about some math I've done around concepts around behavior and networks and disease spread and transmission. And it's going to take some concepts that you've heard in each of the other talks that you already heard today and yesterday and take them to a slightly different direction in a slightly different way of writing them down, and then a slightly different way of interrogating them. And it'll either be with slides or without slides. So we'll find out shortly. I can totally do this without slides if I have to. Equations are better when spoken, right? Yes. Okay, so also I do promise that if we do get the slides, there are some equations on them, but you can ignore them entirely. Ooh, thank you.
Hey,
thank you so much.
I did nothing.
Awesome. No, karma. Thank you. Amazing. Okay. And does this? Yes, it does work. Excellent. So we heard about a lovely talk on diffusion in networks, and we had some insights already into diffusion processes. And yesterday you heard a little bit about what in my lingo would be the Kolmogorov 0-1 law, that threshold of like underneath this threshold nothing gets through, and over that threshold everything gets through. Yes? Yes? Yes. Yes. Excellent. Thank you. Ooh. Other than not dying, it's going to be fantastic. We're going to do participatory. It's like, how many people have ever been in either a religious service or a social group where call and response?
Amen.
Amen. Yes. Excellent. I accept amen. Okay. So that's what it's going to be like. So the basic definition of transmission, so diffusion is one characterization, but the basic definition of transmission of all things is a thing goes from one individual to another individual. This is a terrible definition, especially if you're a mathematician and you like precise things, but it is actually also terrifyingly what's in most dictionaries. So when we say a thing, we mean a property, a possession, an idea, a feature, a state. A thing goes from one individual, that could be a person, it could be a gene, it could be a city, take your pick, to another individual through some process of transmission. Okay, so it gets interesting when there are choices or behaviors involved in this. It's less interesting when it's just a neutral percolation process. It's still interesting, but it's less interesting, I'm going to argue. I'm going to argue that the fun parts come when there are behaviors or choices. And I don't mean to anthropomorphize cities, but actually, yeah, I do. When I say choices, I don't necessarily mean that it has to be with conscious thought, but I do mean that there has to be some element of stochasticity and some element of determinism based on condition. Yes?
Yes.
Yes. Yes. Awesome. Thank you. I also accept amen. So, and so common examples, and you've heard about some of each of these today: infectious diseases, spread of information, persuasion and influence, take your pick. So, and I'm going to propose a slightly different categorization, but very much related to what Jim said earlier today about interesting diffusion processes. So I think there are interesting aspects of network influence that come from the structure itself, whether that is a static structure because the thing is actually not changing, static because it's meant to capture an aggregate of dynamics, with a disclaimer that there's some provably cool things that happen when you have a convergent static description that is meant to capture an ongoing dynamic that aren't the same thing. And you get really different diffusion dynamics in that sense. And I can now prove why, although the proof is not in the paper I just cited at the bottom of the thing. But if you're curious about why that happens, I can prove it to you. Or the network itself is dynamic, but it can be dynamic in structure. Nodes change, edges change, but But we're still talking about the structural properties of the topology of the network. Or we can talk about processes on the network. And diffusion is one process that happens on a network. It's not the only process, but that is constrained by the topology. Otherwise, we wouldn't formulate it as a network question. But that can be deterministic or stochastic. And the processes can get really complicated. And so today, we're going to finish out the day by talking about processes of transmission and generalizing those and making them really weird and complicated. And we're going to generalize network structure so that we're not just looking at pairs, we're looking at higher order things or coupled things. All right, also jargon. We've talked about a bunch of these already today, but I'm going to use the jargon that I come from, which is math and complex systems and self-organization. So we can have, of course, network changes that affect processes. So in this case, we add a link between these two guys, and then this guy has the opportunity to convert that guy to being read because that link got added. But of course, the processes then affect the network structure itself. And so that guy, having turned red, may decide to get rid of his connection to other yellow guys and form new connections to red guys. Yes? Yes. Yes. Excellent. Thank you. OK. So my favorite questions are about self-organization itself. And that is when we have fully coupled systems in both directions. So emergent properties are ones that happen because everyone has a rule, and you watch everyone follow the rule, and then you say, OK, what happened to everybody together as a collective? So here is a co-location by daily routine network. Everyone has a, like, here's where I go during the day. And then you look and see, did they show up at the same place? And then you create a network that way. That's great. It's emergent. Everyone's got a rule, but it's not necessarily self-organizing. Self-organizing is when everyone goes, how am I going to make my choices about what I'm going to do today? And that's going to depend on what other people are doing. And so things like preferential attachment. I'm going to make friends with the popular people. Well, why are they popular? It's because other people made friends with them. Everyone get the difference? Yes. Great. OK. All right. So self-organization, it can lead to really cool things in just the structure, but also the dynamics of networks. And I'm not going to go into this. I'm going to tease it, because most of the interesting parts of this are math. So if you're interested, instead of me boring you about it, what I want to do is whet your appetite and get you going, oh, that would be cool. And then if you're interested, come talk to me, because these are the sorts of things I like to do. So for example, you can create networks with specific link densities by a pure process of emergent self-organization. In this case, we called it propinquity, because, I don't know, we wanted a catchy word. You can use self-organizing strategies to restore function. So this gets to a little bit of that idea of a goal measure for the outcome. But instead of that being structural for us, we said, what if our goal was this process that lived on top of the structure? How do we get that by making structural choices? You can classify emergent structures. So everyone remember the periodic table of triads from yesterday? Right? If you generalize that to, instead of being triads, it's just induced subgraphs on n vertices, and then you look at sample subdensity, you can classify where networks came from. And that's all because of emergent self-organization. So I'm going to not tell you about any of those other than they exist. But everyone with me on they exist? Yes. Yes, excellent. OK. So things are even more fun when we need complicated networks to capture the behavior. So today, the actual things I am going to talk to you about, we're going to talk about what we need to do when the complicated behavior we want to capture is about individuals. And then separately, what if it's about processes? So the first one is an example from COVID research, because why not? And some of it is amazing work with Jim and with Dana. And some of that work is being generalized by Katie. So people in the room can back me up on this. I'm not the only person you can ask questions. But the idea comes from that idea of the structure and the behavior feeding back and forth. And in this case, we're going to have a multiplex or multi-layer network. And the idea here is that, yes, people live in communities that talk to each other. And so these guys sort of have, each color has similar beliefs going into an outbreak of how much is a disease dangerous, how much do I hate wearing masks, things like that. But people also have multiple ways of observing the world themselves. And so they can live in the world where they contact each other, which is how you actually transmit disease. But they can also talk to each other. And when they talk to each other, they can talk about disease. But you can't actually catch COVID over the phone. Right?
Right.
Right. Yes, thank you. You're rapidly becoming my favorite person. But these layers interact because humans calibrate our understanding. We are creatures that have the social construction of risk perception. When all of us react to things, we're not doing it because we are scientists. It would be lovely if we did. I would be so much happier. But this has happened to all of us in some context or another. A new thing happens, or a sudden noise happens. And what's the first thing that you do if you're in a crowded room? First of all, you probably sit up a little bit straighter. But then you probably look at everybody else, right? And you go, I don't know what just happened. Does everyone else know what just happened? And you don't actually say that. What you're actually doing is checking for nonverbal cues of everybody else's posture and comfort. And if everyone else looks completely calm, then there are two explanations. One, you've just lost your mind and only you experienced that thing. Or two, everyone else experienced it, but they are not panicked about it, and it's probably fine. Right? Now, either of those two things could be a big problem. Right? I have lost my mind, not generally a great start to the day. Or everyone is calm about this. Sometimes that's fantastic. It means everyone knows what's going on and it really is okay. And sometimes that's terrible because the world is about to end and everybody else is fine with it. Right? Those are not good mismatches. But on average, as a heuristic, everybody else being mostly okay with something tells you when you can be mostly okay with it. Right? This is also a great indicator of whether or not you're in trouble with someone else's parents. Right? If you remember either being a very small child or going home to meet your significant other's parents, right? You don't know what the signals are for danger. The person who's the kid of the parents does. Right? So you're constantly cueing off of them. Those signals can also be wrong, especially like if you remember going home to meet the parents of your first significant other, right? That person's signals for themselves of how much they're interpreting their parents' signals about the approval of the potential significant other, not yet well calibrated, right? So the fact that we're talking about perception and not reality is already important to capture. This is the kind of thing I love putting in math, where we go like, okay, we need an us, and we need a shared agreement of what we think, and it needs to come from what we all individually started believing, and some observations that may or may not be flawed, and then we need to have consensus that may or may not be accurate, and then each of us needs to go, okay, I think I know what you all believe, and therefore that's how I'm going to behave. Right? If you think about how many steps were just involved in that, this is some bullshit. Right? But it's what humans do. So we made a model of this for COVID. And we said, okay, in your communication layer with your cell phones and your internet and you're watching the news media, you have some layer of communication with your neighbors. And in this case, it's network neighbors, not physical neighbors. And that can either reassure you, in which case your concern about your own safety goes down, or it can prime you. You can be more scared, in which case your concern about your own safety goes up. And then you decide whether or not you're going to behave in accordance with a particular public health policy based on your level of concern at the time. And then from that level of concern and communication with your neighbors, it's both going to feed into and feed back from things. There's also going to be an infection layer where you physically go touch people or breathe on them, and you can transmit infection or catch infection. And then you're going to change your disease status to I caught the disease or I didn't, or I recover from the disease if I had it. And then everyone is going to update their concern with their neighbors because some of them saw diseased people or caught the disease. So there's input to how reassured I am and concerned from my communication layer, and influence from disease status into the layer of concern for communication. And then there's going to be adherence of communication. Do I watch other people do the things? And then we can get reassurance effects. So everyone has seen some of those wonderful studies where like we wear our seatbelts and therefore speed more? Yes? Oh, okay, maybe. So I don't know if that's because you guys aren't responding or because you haven't seen those studies. It turns out making everyone wear seatbelts increased the average speed at which people were willing to go over the speed limit. That's an interesting health problem, right? But again, turns out we're all humans and we're mostly stupid. But that's okay, we can overcome it with work. So everyone has done something like that, right? Even though we don't say it that way. We go like, oh, I did the protective thing and now I can do the other thing. I exercised really well and now I'm going to eat the ice cream, right? Okay, excellent. Good, you're all human. Okay, and so now we feed that back in a loop, and now we can ask, we wrote way too many papers about this model, but more cool ones are coming out soon. But now we can ask things about, well, if this is what's happening in these two layers, how tightly coupled do the layers have to be in order to really influence things? Can we tell anybody anything in the news anymore? Does it matter how strictly segregated the initial communities are? And we can ask all those kinds of questions. And the important thing is there's a separation between those two layers, especially if you're going to ask things like urban-rural divides. Because it turns out that the children of people in rural areas move to big cities. And it turns out that if you're going to do things like public health interventions, big cities have very different risk tolerances than rural villages. Right? Yes. All right. So, multiplex networks. Yay. This one was just 2. You can have many. Then you have interesting questions about what's happening within each layer and across the layers. And that's how you get weird things like this. But really, I'm telling this to you both because example of multiplex model, but also crazy-ass complicated rule system. Right? No problem in making this an actual quantitative model and then poking at it. Some of this has real data behind it now because we were lucky enough, back in the before time when science was funded, we were lucky enough to partner with some incredible economists at University of Wyoming who did some survey data and looked at some economic data and travel data from multiple countries, basically generalizing and parameterizing exactly this idea in these layers. And that was incredibly exciting. I don't do data. I work with people who do data. I have no idea. I do this part. All right. Here's where you can do this part. Based on things like, so first of all, the code for exactly that is available. It's not beautiful, but it's available. But working with our again, in the moment right now, we still have a pandemic science center. Not going to guarantee that's true tomorrow. But today, we still have a pandemic science center, and as part of that, we have been working to make what we're calling FlexSim. And the idea of FlexSim is that it should be a choose-your-own-adventure model that you can run really fast to integrate these kinds of features and behaviors. So in the base model, you have health transitions and weights and probabilities of diffusion. You have population structure, so how many communities? How close-knit are the communities? In what layers are the communities talking to each other? What are some population traits? Is there demography involved? Are people younger in that community and older in that one? Disease modules. So this is the epidemiological and etiological properties. So how infective? How susceptible? What are your exposure risks? What are the transition weights for the timing of disease? This is all compartmental. So we've got mass averages. But you can subdivide. So if your mass average is too coarse for that whole population, make a new population. Tell people in this model that there's another community that looks exactly like this community, except different age transitions. Yeah? Yeah? Yes. Thank you. Awesome. And then we have a resource model, because we thought building in some economics would be nice. So the actual physical personal protective equipment accessibility, but also social distancing, also risk sensitivity, also how much does any of this cost? Are there opportunity costs from going to work? These are all features that get built in, and because it's modular, there's the, I don't know what comes next. And that's where you guys also come in, because your guys' suggestions tell us what to develop next. But the cool part about this also is, once you select which modules you want in your model and put them together in that choose-your-own-adventure way, Then you feed in your parameter values for each of your selected things and go, OK, build and simulate the damn thing for me. And we had an incredibly talented programmer who was able to make all of this work so that populations of over 1 million for a month of days can run in about 5 minutes. So we're really happy about this. And right now, we are in the final stages of making the front end pretty. But the code for it is accessible now. So if you happen to not mind digging into this is terrible to run, you can run it right now. And hopefully, in another few months, there will be a nice user GUI that you can just use the damn thing. And if it's small enough that you can do it, you can probably run it on your laptop. And if you really want populations in the size of millions, send it to a local cluster, and it'll be done before you actually close your laptop from sending the process. So that's kind of cool. Yes, ta-da. Shameless plug. Yes, thank you, jazz hands. Huzzah! OK, so we are working on making it pretty. The code and documentation are currently available on GitHub if you ask. They will be made publicly available without having to ask, probably in a couple of months after we're truly sure we've cleaned up everything. And then we are working, Jim included, working on making good user interfaces for the front end. But also, if any of you happen to code in Julia and need an extra side hustle, we can pay someone to help with this. So if you or your friends would like to help with this, please come tell me. The back end is all coded. It's just the front end that needs help. And then once it's available, the code will be accessible via appex.org, which is our website, which will continue even if the center doesn't. So, all right, questions on just this bit? OK. Is that because everyone's, oh, I'm sorry. Thank you.
Yeah, I was curious.
Thanks.
Kind of the adherence and behaviors. I've usually seen models where it's kind of treated as like someone has like a constant adherence at like one point. Like I'm thinking about COVID. Like perhaps my adherence now is not the same as when it was in like 21.
Yeah.
And so does that account for it just within like a separate compartment? Does that account for it within?
So the way that these modules are working is that it has to do with some of the disease module and some of the resource module and some of the population module. Because what it's all being built on is this stuff, which, how many people here have taken a social psychology class? Awesome. So all of you, because you're completely on your toes, will recognize that this is the theory of planned behavior. Right? Oh, I didn't get a single amen. Right? Right. So we have perceived social norms, and we have perceived behavioral control, and we have values and beliefs, and we have well, I was phrasing something as value, belief, norm theory, but still basically the same thing. There's no actual social psychologist in the room to hurt me, right? Excellent. OK, so the answer to where does a shifting adherence come in is shifting adherence gets built by this level of concern, which gets dynamically updated by both your communication layer and your observation of the disease layer. So everybody is continuously updating, well, in the simulation case for this guy, it's discrete. But in this one, it can be a continuous update, because this was for very small simulations. A continuous update so that concern is individually calculated as a continuous update, and you can even do it with PDEs. So I think the code available for this model is a discrete simulation. But we will get in a moment to how to do that without the discrete simulation. But yeah, great question. Thank you. Other questions? All right, thank you for the assistant noticing the question. My apologies, but awesome. Yeah? Awesome question. Thank you so much. So for this model, The answer is there needs to be pre-processing for you to extract hypothesized parameter values from your data. This very much is biased by the people who started it being on the mathy side, not the stats side. So the definition I always give to my students of what the difference between mathematicians and statisticians is a statistician starts with data and goes, what does it tell me? And a mathematician starts with a process or a function and goes, what data would it produce? And so this is built very much from the what data would it produce, starting in what is actually a pretty solid theory from social psychology, and then matching it to, I'm not even going to say validation, matching it in a qualitatively satisfying sense to some observations in both behavioral adherence and infection patterns for not just COVID now, but multiple types of outbreaks, to see whether or not we get, again, qualitative human satisfactory agreement with like, yeah, we haven't missed anything too bad. We could still have missed a lot of things, but no, it's not the case that you put things into this and then get values out for the parameters. Thank you, it's a great question. Other questions on this stuff? All right, awesome. So notice that because it's modular like this, you could actually use this as just a belief update network without any disease. I've presented it to you as an epidemiological simulator. It could also just be a persuasion argument between multiple communities, and something is being observed. It doesn't have to be a disease. The adherence doesn't have to be to personal protective equipment. It could be wearing an I voted sticker, right? It could be wearing a particular color hat, right? So anything where there's a different observable feature of the universe around you versus a communication feature of your friends and family that you talk to or the news talking at you to calibrate that understanding of a social norm. And again, it's a perceived social norm, not a real social norm. The difference can be very meaningful, right? If nothing else, right? I think the statistic in the US is 72% of drivers believe they're better than average. Yes, we're smart. So while I'm presenting it to you as an epi simulator, it really can be a social dynamic simulator for the idea of multi-layer network collaborations in some kind of shared understanding and how individuals react to their perception of that construction of the shared understanding. So I think that's pretty cool. All right, so ta-da! Complicated things individuals do. Okay, what happens about complicated processes? I actually think this one's even more fun. All right, so in the FlexSim model, we made a really strong simplifying assumption that has been the underlying assumption for most of the things that we've talked about today. Not all of them, but most of them. And that is that contact is happening between pairs. But already, even in FlexSim, and in some of the other things we talked about today, in complex contagions, what we're doing is actually trying to get a function on a group of individuals. And what we've done up till now is sort of assume that, like, oh, you'll just look at all the pairs and then figure out some function on the existence of the pairs, and then we'll go from there. And I'm going to argue that that misses a whole bunch of opportunity. So the easiest way to see that this doesn't always work is to ask this question. If I tell you that this is a network of 4 people talking to each other, and then I ask you these questions, none of you can tell me the answer. I'm just going to assert that. Did each pair talk? Maybe, right? Depends on what I mean by this. Did they meet and talk as a group as a whole? Maybe. Did all 4 hang out, but 2 of them were already couples going in? Right? So some of you have been to a party with friends? Yes. Yes. Okay, seriously, right? Has anyone not been to a party with friends? Okay, but right, the dynamic of how you hang out with your friends changes if you show up with a particular friend you came with, right? That could be your significant other, but it could just also be the person who came in the same vehicle as you, right? There's some understanding, there's some interaction with the rest of the group that you guys are operating as a set. And that set is happening within the broader context of a bigger set. And there's a different dynamic, right? And you've probably also, how many people have been the uncoupled person in a room of otherwise coupled people? Yes, right? And there is definitely a moment where you're like, oh, there are so many like knowing glances and inside jokes happening, and I am I'm just here. Okay, right? And that's a really different dynamic. And so being able to start writing down and building models and then building quantitative, rigorous, and interrogable, why can I not say that word? So that you can interrogate, we're going to bypass the problem, so that you can interrogate those models, starts being really cool. So how do we do that? Well, what we want is something that's going to capture multi-way communication, so that if 3 of us are talking together, I can represent that as different from I talk to 2 other people who talk to each other also, right? We want explicit substructure, so that if 3 of us are talking, but 2 of us are a couple, I get to know. We want to know how the group together functions and connects. And we want a generalized network. So all the tools we have in networks, we want to be able to put on all of the things that we want with the features with the multi-way collaborations and the explicit substructures and all of those good things. So my research group has published a bunch of these things now. How many people are like, yeah, I've seen hypergraphs? Yeah, OK, this is basically hypergraphs, but we're going to use slightly different math notation for reasons of my own sanity. So has everyone heard of hypergraphs? OK, great. So the idea of a hypergraph, right, is just instead of drawing a line between 2 points, you draw a bubble around a group of points. And it could be anywhere from 0 points, in which case your bubble is empty, to all the points in the network, in which case, congratulations, it's a complete graph. Right? Awesome. OK, so what we're going to do actually is use simplicial sets instead of hypergraphs, because hypergraphs have the weird following substructure problem. It's very awkward with hypergraphs to write down whether or not your bubble is around itself other bubbles. You can do it, but it's really annoying. And instead, if you think about simplicial sets, it becomes beautiful and automatic, and all the notation just melts away like candy. It's fantastic. There is something, just a warning, if you like what I'm saying, come to the dark side and play with me. But be warned, there is a thing called simplicial complices. And a simplicial complex is a simplicial set where if I have one higher order group, it is guaranteed to contain all of the smaller groups that could be within it. That sucks. We don't want that. It's great for things like figuring out where you should build more cell towers. It is not good for sociology. I will assert that. All right, so simplicial sets are these beautiful objects. Now we can write, now these are pictures, obviously. This one breaks my mind a little bit. Honestly, pictures break my mind a little bit. I'm the least visual human to have ever lived. But equations make me very happy. So I promise not to throw too many at you. But now we can fill, essentially what we can do is color in faces. So the face of a tetrahedron is a triangle. In this case, I have written down a darkened line on the triangle that are the edges of the face of the triangle. The filled-in triangle tells me that these 3 guys talk to each other as a group. Each of these darkened edges tells me green talk to yellow, separately from the triangle green, yellow, blue. Right? Now I can write down this guy, and that tells me something different from this, and more specific. And in case, is anyone here actually an equations person? Oh, an equations person. OK, I'm going to skip this then, but it's really beautiful. Just trust me. OK. OK, so when we move to simplicial sets, now we can do even more interesting things. So we can, for example, have functions on sets. And those functions on sets can take as arguments, for example, the subsets. So we can ask things about, well, is the transmission dynamic that you want on these sets one of learning, where this person has information A and this person doesn't, and then A is transmitted from that person because they were in a set together? Or instead, is it discovery? This person knows A and this person knows B, and together they discover C. But this person doesn't wind up knowing B, and this person doesn't wind up knowing A. But now they know A and C and B and C respectively. We can ask about group makeup and multiplicity. We can say, well, Here's a case where there's a bubble with 3 people who know A and 1 person who knows B. But that may not be the same as this bubble where 3 people know A and 1 person knows B, but that guy who knows B is in a different bubble with 2 people who know A. Right? And especially if you're doing things like building a model of, for example, research networks and collaboration networks and how people arrive at innovation, these 2 things may be vastly different. Right? Especially if B is critical to the thing that's trying to be discovered. So now I'm anthropomorphizing the future sense of science. I'm comfortable with that, actually. We can also talk about the nature of knowledge. So we can have categorical knowledge, where there is depth of I know things A1 and A2 versus breadth, I know things A1 and B1. Or ordinal, I have to know thing A1 before I can know thing A2, I'm learning. Or cardinal, A1 and A2 together get added, so there's some actual function of the cardinality of what is known. And of course, now we could go back with that picture to these guys and give each of them what type of knowledge is this and what can you do with it. So now we can explore things like complex contagions on sets with subsets with different types of knowledge and learning rules. So that's very easy for simple contagions, the ones where just I am connected to somebody or in a bubble with somebody who knows this or has that infection, and therefore with some probability, independent of everything else, I catch it or I learn it. Versus complex contagions, where there's some kind of threshold or more interesting function that says some percentage of my network needs to have knowledge of this before I can learn it, or before I care about it, or before I can catch the disease, which does happen, by the way. The conversation we had yesterday about like, just fight your reviewers, and if you're righteous, you'll win. I have a paper right now that we literally got, I'm so bitter about this. If anyone has an idea for this paper, come tell me. But we just got rejected on appeal because we had 2 reviewers that said accept with minor revision, and 1 reviewer that said this paper must be rejected. There is no way to write any kind of transmission process that is not about a pathogen in biology. And we were like, okay, but we're talking about psychological states. And so we appealed it, and the editor was like, nope, the reviewer was harsh but fair. Okay, so I'm currently pissed off at that journal. But you can write... I'm sorry?
Amen.
Ah, thank you, yes! God, reviewer 2 must die. But sorry, I don't know if everyone has seen that meme. I did not mean my specific reviewer 2, I mean the meme. Okay, good. But yes, thank you. Amen, brother. Okay, so now the idea, though, is we're not just talking about complex contagions in the sense of percentages and thresholds. Now we're talking about complex contagions in the sense of what does the set have to look like for transmission to be successful? And at what level of success? I can talk about learning some things. So clearly we can do basic biological pathogen transmission. Whoops, there we go. So here's an example of that we published, just showing that we get differences from this. And if you need, probably you don't, but if you need the biological definition of why, the answer is it's called dose-response curves. If I cough 7 virions at you, you're unlikely to get sick unless it's norovirus. Norovirus, it turns out 7 is the magic number. 7 individual particles can transmit norovirus. There is no known reason why we don't all have norovirus all the time. So, but if it's not norovirus, it can take tens of thousands of pathogenic particles reaching you within a time window to both be sufficient to colonize you and overwhelm your immune system such that you then catch the disease. And for example, at the tail end of someone kind of like clearing their throat after feeling much better, they're probably not producing that much virus. And at the early stages of someone just catching the infection, they may be starting to shed, but not a lot. And so maybe what you need is some set of individuals shedding each enough that together they can give you the disease. But if you don't get that within a time window, you're fine. Either your immune system fights it off or it fails to colonize you entirely. Right? Yes, thank you. We're in the home stretch, I promise. All right, so if we do that, we can actually just calculate differences between what it looks like if we have just a network representation and what it looks like when we have the difference between who gets infected, more if we've got a simplicial set representation versus an independent probability of infection per contact. And most of the time, the simplicial set version will overrepresent infection relative to the dyad. But sometimes the dyad is worse. You can't really see, but it's blue right in there. And so we can start analyzing why did that happen and when. And the answer is we made this up. That's why this. But we can also talk about things like adding demography. So here's one we just published looking at complex contagions of higher order networks where where the behavior of the structure and the transmission of the information were dependent on demography. We modeled it on elephants. Everyone like elephants? Yes, thank you. Elephants are adorable. Okay. And the details don't actually matter other than to tell you that what we did was look at higher order structure and group composition and then build a function of transmission on the group composition and look at the influence of birth and death and preferential attachment that changes over age, because elephants do that. I'm not an elephant expert, but I play one in this paper. So it's a lot of fun. Now we can build, and I promise you don't have to read the equations, but now we can build different functions that take as arguments the sizes and the styles of the sets, and then we can tell you how to calculate them. So here, I have to tell you, okay, this is going to be a learning rule. Remember, learning is when someone knows thing A and then tells someone else thing A. And the distribution is going to be neutral. My initial, who knows this initially in the network? Just going to randomly throw it at the network and be like, some people know things. It's going to be makeup invariant. So I'm not going to predicate that random, some people know things on any features of the individuals. I'm going to say that this one is cardinal information. Why not? And I'm going to say that there's a cardinal structure. And I'm going to say that there's a gain trajectory. No one's going to lose information. We're just going to add information that you know when people tell it to you. And it's going to be simultaneous timing. So this is going to update in discrete rounds. And everyone's going to learn stuff at the same time. And then everyone's going to learn stuff at the same time in the next round. Right? But we could instead have been like, no, we're going to pick an ordering. And then that person learns first. And then that person learns. And then that person learns. Right? So we start telling more and more things in the function. And now we can say, well, how about delta smartest? So here in this rule, which again, you don't have to read it all individuals gain knowledge depending on the difference from their knowledge to the most knowledgeable person in the bubble that they're in right now. And notice I can be in multiple bubbles. So that's also where the cardinal structure and simultaneous timing come in. Which bubbles do I calculate at once? Right now, all of them. Right? And then we're going to take, because it's delta smartest, we're going to have a rule for what the maximum that person learns from any of their bubbles. But that's not the only rule. We could have we call this proportional fixed gain. Proportional fixed gain is individuals within a particular subset gain an equal portion of knowledge F. So we're sort of dividing up the knowledge and handing it to folks. The subset of individuals that change their knowledge value are calculated based on the proportion of the set that has more knowledge than each individual initially. So again, that's going to be upward or mixed trajectory. But it can't go monotonically down because everyone's learning something, right? But you can get confused. You can fail to learn right now. We can have smartest only. We really shouldn't have called it this, but we called it smartest only. Of the available knowledge, the smartest individual in the group teaches everyone else what they know. And everyone else gets it. So, okay, actually I'll stop there. So these three are not important at all. What's important is the idea that I can stand here and say to you, here's how we would write down some math that does these different types of functions on these simplicial sets. Right? And right now, I made those rules that I showed you simple enough that they didn't have things like how many simplicial sets of smaller size were inside the bigger set. That's a structural question, right? Those were process questions. Now we can start asking structural questions. What kinds of structural questions do we want to ask? Well, they look very much like the ones we want to ask on networks. So here is a higher order networks version of clustering coefficient. Here's one that's just local clustering coefficient. It's how many closed groups exist right around me. And again, No one's an equations person, so ignore that. But locally, just look in an immediate neighborhood and ask how many closed groups are there. Now it's not triads, now it's sets of any order that are represented locally. But instead of it being local, I could then ask, well, how does this connect to other things in the higher order set? So I could say something like, what about next order clustering, where it's the proportion of closed groups via faces or simplices. So a face is that colored in polyhedron, but then the simplex can be the uncolored in, think of it like a bubble. Everyone has at some point blown a bubble, like a big one? Yes. Excellent, fantastic. You know that it sort of snaps back to whatever perimeter you've used to blow the bubble. Think about a simplex like that. So now we can say, oh, all right, well, what's the proportion of closed groups via faces or simplices? And then we can generalize next order clustering so that we have a next order clustering coefficient over the whole set. These are also not particularly important, right? So yes, there are equations, but what I'm telling you is we can write things like this. So in the same way as centrality is not being particularly important, but it's very important to go, what do I want to measure and how do I do that? Start thinking about these things. We can also ask, here's the one that I talked about a minute ago, subsimplicial density. What proportion of subsets of a current group exist inside the group that contribute to it? Not just how many pairs or triads are there, but how many pairs or triads are critical to the construction of this group of 30 people. Right? This group of 30 people would not exist as it does now if inside this group of 30 people, those trios and duos were operating as separate groups also. Right? And that can be incredibly important. Right? How many of you have ever worked on some big group project where you divided and conquered? Yes?
Yes.
Yes-ish. Okay. Some of you decidedly yes, some of you maybe not. But right, sometimes those go really well and sometimes they crash and burn. What if we could start predicting by who's forced to be in groups with whom, or how many groups of which size had to come together? This is actually work I did for the US Army for a while, is figuring out what group size you want to set particular warfighter task groups to so that they get it done and can rely on each other and then can remeld and do it efficiently. All right, sometimes subsimplicial density doesn't matter at all. It depends on so that's a structural property, and it depends on what kind of process you have on the structure for whether or not it matters. So here's static participation and here's dynamic participation, because we can have static and dynamic structures for simplicial sets also. And in this case, we used a difference in mean knowledge over iteration, just to demonstrate that, like, well, here's a final knowledge with an increasing subsimplicial density, and we get some interest in dynamics. We sort of get a little bit of stratification, but here we get very good stratification. Doesn't really matter, but the idea is ask questions like this, and we've got the math for it. This, again, notice that this means that the usual idea of, if you see the word simplex on expectation in an applied math paper, it's about a simplicial complex, and this doesn't work. So yay for simplicial complexes, but not about this question. You need simplicial sets instead. I'm going to bypass that. OK, so we can ask particular questions about correlates of different processes and different structures, but that's not the point. The point is to start thinking about these kinds of higher order networks and then the functions that we can write on them that take them as arguments. And there is an R package that will be released as soon as the paper is accepted with the most recent of these that does all of the calculations I just showed you. Subsimplicial density, local clustering coefficient, next order global clustering coefficient, and at least the 3 learning rules that I showed you, plus a couple more. So hopefully coming soon. This one has not yet been annoyingly rejected for no good reason. It's been annoyingly rejected for good reasons, and we're fixing them. But OK, final moment of this. What if you like this idea, but you don't want to simulate shit? How many people don't like simulating things? Oh, only that number? Okay, that's pretty good. Well, the rest of you, please keep simulating everything. But
We'll bump those two out soon.
no, we'll convert them. It'll be great. No. So up until now, I've talked to you about things that do have to be calculated computationally, as opposed to proven analytically. We can start proving things analytically. This makes me so happy. And that means that they're also much faster. So my incredibly clever former graduate student, Maggie Sullins, came up with a brilliant way to use probability density functions to be able to describe the distribution of different sizes of sets in what is otherwise a homogeneous mixing compartmental model, and say, what is your probability that you are going to interact in this network with a group of size 6, separately from what is the probability that you're going to interact with a group of size 5? And write down each of those probability distributions, and then use them in an ordinary differential equation to capture the simplicial set structure of your population in a way that is then incredibly rapidly calculable using just ODE solvers in MATLAB. So, and code to that is absolutely available upon request and will hopefully soon be associated with a published paper. But that is in review. And I will not walk you through those equations because no one's with me on this, but I promise they're beautiful. Here's an example of a paper of a result from one of the papers. This was about stress. I think this one is actually the one that Katie is also on. Yes. So Katie can also answer questions about this because she's awesome. But what we were doing was asking, well, if people are experiencing stress and then helping each other get over that stressed experience, what do those dynamics do? All right, so that was our example of what about complicated behavioral processes. So we did individuals and we did processes, and we talked about structure and we talked about dynamics. So here's a shameless pitch. If you like this, I'm absolutely hiring a postdoc in this right now. So either come talk to me or tell your friends. And then here are all the incredibly awesome people who either work with me right now or have worked with me on stuff I presented to you. And thank you so much. Questions? Beautiful question, thank you. So I don't know if everyone could hear, so I'm going to repeat mostly for the tape. But so the question is, if I understood it correctly, was, look, in traditional networks, we have community detection, and that tells us how to group individuals into what we could think of as bubbles. How is that any different from these idea of sets? Yeah? Awesome. Okay, so here's the answer. Communities in traditional networks are, as I understand it for the literature as you guys talk about it, defined by an arbitrary boundary such that the internal density is larger than the connection from that with internal group to the rest of the network. In that sense, this is generalized in the same way by defining the idea of local clustering coefficient to discover that, but that is different from saying, here are the sets of individuals that interacted. In the same way that you would not define a community to be one dyad, one pair in a network, right? You say, oh, the edge exists between those two or not, and then you ask, is that edge part of a community? Or should we build a community by increasing the edge density by triadic closure or something else like that in the more generalized structure of the network? For hypergraphs and or simplicial set formulations, the same thing applies. It's not that you're saying that there's a greater density within that particular bubble. You're saying that bubble is the operant object. And that bubble is of any size, and it has, in this case, because we want it to, and this is again the difference between hyperedges and simplicial sets, it can have heterogeneity in how individuals participate. So in a simplicial set, I can be part of the set, and the pair, me and my friend, can be part of the set. So Dana and I might be a set, and Dana and I might participate in a group, and separately I might participate in the same group. But when Dana and I participate as us together in that group, we're operating with different information. And so in the same way that an edge in the traditional network is part of a cluster or a part of a community, but it is not the object of the network. It is something that you then analyze about the network. The object of the bubble around individual subsets or individual nodes that comprise the set itself with no subsets, those are the objects of the simplicial set construction. And then you analyze it in the same way to detect community. Thanks. Yeah?
How would you structure data collection in a way in order to capture those individuals? I think you brought up the example of like, well, in a neighborhood, there are different like groups and communities functioning. Are they interacting with each other differently? How are they operating in those spaces? You don't know a ton about those communities. How do you reach essentially like a point in place where you have enough people in that set in order to make meaningful inferences about how they're interacting within that set and with other sets?
Awesome question. Thank you. So again, I'm just going to repeat it for volume. So the question was about data. How do you collect enough data or know when to collect the data about belonging in higher order sets rather than just networks? Is that a fair? OK, awesome. So in some sense, the answer is it depends on whether or not your interrogation is meant to be discovery driven or hypothesis testing. And so I think that the actual fun part of all of this is closer to when it is hypothesis testing. Because, for example, you could say, and we've heard in some cases from some of the interrogations earlier today, in this data, this thing we would have thought was explanatory wasn't. And the answer to that could be, yeah, maybe that's in that data it's not. Or it could be, could some higher order things be happening? And so how do you go get the data about that? The answer then is, if you know what you're looking for, then those are either questions you can ask in surveys. There are some, there's some animal social networks work that I don't particularly like that does proximity logging and just assumes if you're close by each other for long enough, then you didn't move apart and therefore you were purposefully together and therefore you must like each other. I do love, so there's some work that I have done now that I do actually like on songbird cultural norms. And that is actually by both who can hear each other and then who reproduces each other's types of trills. And that is influenced by a higher order group. You can meaningfully hear each other as they calibrate. Go like, oh, that wasn't just these two talking to each other. That was these two because they also hear that guy who's also talking to them. And that is quantifiable data of, oh yeah, no, you need the trio to get that. But then there are lots of times where you can't. And I honestly don't know. But my hope is that by being the theorist and going, this would be cool, then very creative people who do the empirical side can start designing controlled experiments to try and figure it out. So I know that's a cop-out.
So an even more basic question on the same point, I think, which is, what does the actual data file look like? So how do I record data that would get me to be able to use these tools?
Absolutely, thank you. So what does the data look like? The answer is in the same way that you might write down a vertex set and an edge set in order to capture a network. In this case, you write down a vertex set and a simplex set. So instead of just listing all of the vertices, you list all of the sets that contribute, and then those sets include or can include subsets. And so from that, then you start populating. Instead of a matrix, it becomes a tensor, which is just a fancy word for a more dimensionally rich matrix. But then it's easy to populate. And you can have those in the same way as networks. You can have them directed or undirected. You can have temporal shifts. You can have weighted or unweighted simplices. And in fact, also you can now write functions on the order and weight of the simplex. So you just, the basic information is just a set list. Yes, so yes, the process for that first model was we started with the theory of planned behavior and went, okay, what would theory of planned behavior tell us about how people should react to both direct observation and communication-based understanding. And then from that, we built the model, and then we built some purely theoretical predictions. So the papers that came out of just my lab about that are data-free, zero data. Literally just, here is what we learned from the structure of this process. And let's throw some different types of assumptions about parameter values at it and see how differently it behaves. And then a different team working with us said, you know what, we think we have some actual data that we could use to parameterize and validate this example in COVID. And they did that after those initial models were published.
Thank you so much.
Thank you.
For questions that people would like to ask about anything over the course of today, that's a 2-minute what's the learning model. This is a cardinal learning model, and we want to take the things we learned yesterday, we can add it to today. So whatever you have, let us know. Thank you.
Multiple microphones.
I can take those. Thank you. Please, Suja.
I think here today I hear a lot about this simulating the tie or the pair relationship and how that influences network dynamics. And my question, I think, the question or the phenomenon I'm trying to study or model is down into how to distill it to the question of how to model or simulate the effects of adding or removing key nodes, not ties. And so I'll give you an example and how that may influence the network structure or the structural dynamics. So I'll give you a context. So I study care coordination. One of the things that we know is when patients going through, I study condition teams, and that means oftentimes there are situations where we don't have much of a choice because like primary care providers is an essential node in the network, but they may be moving to another place and be lost in the network, or someone moved from one clinic to another, or loss of insurance and lost that provider, or that they have an emergency of heart attack and have a cardiologist in their team. So there are a lot of these situations where they have to add or remove a key node for various reasons. So my question down to, and I have hypothesis, like, for example, people, if they have a key condition who is more central in the network, meaning have a lot of connections, they may be more effectively forming up a cohesive team later. Or that, if they have past the relationship with the teams in the network. And so they're, or like how they interact with the nodes in the network. So how to model that kind of dynamic?
All right, so that's a longer question than I can repeat. So I'm going to give you but I'm going to try to give a short sort of summary so everyone can hear it. The question is, we've talked to many about the ways in which edges might be removed and how that would the network could get reconfigured around it. And there are settings, like hospital care settings, where nodes of a care team are necessarily substitutable in ways that it might not be perfectly predictable, but are probably understandable because of things like heart attacks or emergencies or insurance or so forth. So there's a system to it. It's not a random replacement of people. There's a reason why they get left. And the question is, what effect would a removal of a node in a network have on the ability of that network to provide care, or the substitution of someone who hasn't been in there before into that care, and how might we go about modeling that? Is that a fair summary? Yes, okay. So my short answer is that this is the big it depends, right? So there's a lot that as a question, as a general rule, I think is probably too big. But I think there are lots of sort of narrower versions of that question that you could then build up into a quilt of an answer that might be different. So my approach is that I can think of a bunch of people in this room that I would like to hear their facet answers on it. But my take would be that there is some sort of extent of either equivalence or behavior practices that can note in effect or out effect that your substitutions would have that would then be able to carry with them. So I carry with me a way of interacting and a way of seeing the world that I'm going to bring with me to most teams.
but that the extent to which that way that I carry it to a team is going to differ depending a little bit on how the team reacts to it. So there's going to be both a node level sort of fixed effects, if you will, to use Bria's language, but also an interactive effect that on the dyad level. And what should happen, I think, is that you would have a bunch of data that could build a model that would describe that kind of idea, and then you would take that model and you'd essentially have a predicted value for people to go for what would happen if I took this person and put it in that team. The problem is it's a counterfactual, much like what we were talking about before, that we don't really have an observation for. And so I would love to hear what you have to say on that.
Yeah, no, it's a great question. I'm actually referencing something we have an experimental data from Chinese high schools trying to figure out what the addition or does to what they try to get at a reasonable time. But I mean, that's probably some of this simulation work on criminal organizations. We try to do with it in a number of ways. It's like you have a trade-off in terms of assumptions you think are most important. So one way you can help it, that we've done in the past with the dark web, is you put a stochastic acronym model to like get anything, and then use that as a basis to initiate anything model. And so you can simulate a particular intervention by removing particular actors, replacing them with a new actor that has new characteristics, and simulate how that will change. The problem is that the counterfactual then, or whatever you're simulating to, assumes that actors' preferences in the treatment and exposure current control conditions are the exact same. So actors aren't changing their transition probability based on this. Now you can't get around that by creating a new model. Like for example, in another study we did a completely slow agent-based model where we actually wrote update the parameters update as you switch actors now. But then of course you don't have the kernel configuration. And so I think there's a real trade-off here. I mean, if you're thinking about what exactly you are willing to assume, and that's what the key criteria is. No matter how you're doing it, you're trying to explore outputs of one actor to another affects the evolution dynamic system. And that could affect how they're actually making sense in the environment.
Other advice for CG on this one? I think, please, David. I think that if I were faced with this problem, this is a great case where you're probably worthwhile spreading your wings past the area you're working on per se. Because I suspect there's been a lot of work done, and I would just intuitively imagine in terms of system substitutions in natural systems. So what happens when you remove one species and another species comes in? Well, that's like what you're doing. Or what happens in a whole series of work on substitute teachers in high schools. There must be some insights from that. Or what would come from the research on exchanging pilots across different places. So there's lots of what are known as multi-team systems literature that has a lot of this kind of work in it. That would make you a way to look at the substitutions of people as they move across multiple involvement in teams. And in fact, the paper we just read, Anna and I just read in our class last semester, was about the ways in which people move across multiple team memberships and how that affects their performances. So there are literatures in the management field, for example, on this in this multi-team systems work. So I think that this is a great example of where the answer to the question you have, asked in a very different way in a very different context, is probably going to be at least hinted at in one of these other papers. And so I would go look there. But the range of answers are really strong qualitative work. Get in there and just ask what people are doing. So Goffman has answers to this as an ethnologist. Or sort of really high assumption questions about substitutability, about how transferable parameters are from one node to a next. How willing are you to make a homogeneity assumption in the parameter application? And that's in some way a testable question, right? So you can try it and see if your prediction's right. But it's one of those things that is, it's too big to do. There is no answer for it. There's a series of approaches for you to come up with the answer that you need that is satisfactory. Any other responses to that? That's a great question. That's a good stump questions. I like that. That's a good. The chumps are stumbling if we're not stumped. So, come back. Follow question. Follow up.
I think I have a lot to digest.
Okay, that's good.
Inspirations how to get more, smaller piece of looking at that problem.
Perfect. Other question. Another question. Someone. Please.
How do you potentially capture like perception-based characteristics, or do you suspect that potentially someone is being like, or maybe not, they're not an accurate narrator?
Excuse me. Those are two separate. I'm not an accurate narrator of my own network at the moment. No. So I think there are two questions embedded in that. So one is a question about what can people know about other people's networks. And the second question is, what can we trust about what people say about their networks? Is that a fair summary?
I can give more specific context.
Okay. Give us more.
So like I'm interested in like loneliness, and there's been like cognitive science work that's shown that as people who are more lonely, they're less likely to be accurate predictors of the people around them on these social ties there are. So then potentially you're introducing statistical bias then between people who think you're trying to test loneliness and people who are maybe less lonely or more accurate. And some people who are lonely are maybe actually relaying fewer ties, or they're relaying like what those ties are, how they're supporting this person. That individual may go maybe inaccurately. And so potentially then if you're trying to study that specific mechanism.
Were people able to hear that? Close enough. All right. So I think that on the question of in the loneliness context, which I think is really an interesting one because you're simultaneously lowering the mean and increasing the variance on the bias side. So the people who have the highest value have the lowest variance in terms of an accuracy standpoint. The simplest non-stupid thing to do, which is always my sort of starting spot, would be to say, just mess with your data and do it and get a parameter estimate. So what you would do is if you think this is a danger in sort of your inference process, add the danger in. So I'm going to add error that's correlated with degree at a certain sort of level and see if it screws up your estimates or not. It might be that the signal is so strong that it doesn't really matter. A less sort of non-stupid thing to do would be to find some way to triangulate the answers that people are giving. And so one of the fields that we haven't had, I don't think we've ever had a session on it here, but it's one of my favorite ways to collect data. It's common in developmental psychology and used to be common in some of the management studies. It's called cognitive social structure data. And what happens in cognitive social structure is you ask each person to describe everything else that's going around them. And you're under no illusion that each person knows what's going on. But the sort of group answer that comes out of that is a much better answer because each person sees it from multiple points of view than what happened if you ask one person to say what just their network is. And so these data are so rich and so beautiful because they allow you to do two things simultaneously. One, you can get a consensus view of the network. So what is the sort of the modal perception of a community? And they've got to be relatively bounded communities, obviously. But then also the variance in my perception of the mean, my distance from the mean, is itself informative. So, being king of the nerds, I see the world very different than being king of the jocks. And so that kind of a situation, how I see the world is in fact a difference in and of itself that changes the way in which we behave. And so I would recommend those sort of, again, the stupid one and the non-stupid one, but there might be other suggestions. Please.
Just to go off that point, I think one of the more fascinating things you can do is try to pair that ego representation around them with some type of observational research to see cognitively do we have a match compared to what we observe. It's to say, I only drink one bottle of whiskey. When you're recycling
Right.
That sort of discrepancy or continuity that can really inform like what's going on socially, and if it matches some type of cultural consensus, right? And if it does, that's cool. And if it doesn't, even more questions.
Well, I mean, I love that because I think that there's always this sort of intuition to say, well, an error is bad, but an error, it's not clear it's an error if it's their perception that's driving. Exactly, right. So I love that point. Please jump in.
There's also a lot of like perceived versus received support literature, especially in the developmental sphere. And usually the developmental folks are like, oh, well, perceived is a lot more important because like actually a measure of how the person's feeling themselves. But received is also important in and of itself. I think it's very technical these reasons. Well, it's valuable to know if this person who is really lonely is actually like severely underestimating.
I mean, I have an elderly relative who is constantly complaining to many of her friends all the time how lonely she is, right? And so it's like, trust me, everyone in your network is tired of hearing about how lonely you are. So so this distinction between behavior and perception is not a problem. It's not an accuracy issue. It's a feature of the system that's worth understanding. Lynn, was that a question? No, sorry. Please.
I was just going to add, like, but it depends, like, what is your question? Because if your question is for the ego, then it is a problem for the ego.
Mm-hmm. Right, exactly. I mean, everything depends on the question, but you're absolutely right. So, I think that we often and this came out of a lot of the work on informant accuracy. When you ask people sort of some of the recent work on what kind of discussions am I having about important matters, for example, it turns out that the things that people are talking about are pretty irrelevant, and the set on any given day might be different, but when you actually sort of track these things over a long period of time, it turns out that people are giving you not an actual answer to the question you're asking, they're giving you an answer to the question you really wished you could have answered, but it's too complicated to ask anyway, which is who are the people who are really important in your life. And it's a way of capturing, we term it in terms of discussion, but it's rarely actually about the discussion. It's about the people that matter to me, and those are the people that come to mind, and something like important matters triggers thinking about the people that are important to me. So there's been some really fun papers that have come out on just that question, right, about how we perceive these things. So. Shift gears, different question. All right, folks. So in an hour, we will be downstairs. It looks like I'm hearing the sound in the room that we should all pay attention to. Is that there's lately been this thunder going on outside. There will be a pizza. There will be pizza and beer and soda, or soda water anyway. Downstairs tonight, 6 o'clock. We'll be there, from 6 until when the pizza's gone. If you are, if you want to join us, please do. And we'll see you either on the deck downstairs, or if it's really truly miserable, we're just going to pull a table inside and hope no one kicks us out. So thank you, everyone. We will see you tomorrow. Is a much more sort of focused on Substance Day, and I'm really excited about this because we have a bunch of returning investigators and former fellows and people who have been working on data collection and modeling and sort of things for a long time in context.